Chapter 11.6, Events involving not and or and odds. There are several ways to express the likelihood of an event. We can also determine the odds in favor and the odds against these events. In this section, we expand our knowledge of probability and explain the meaning of odds. If we know the probability of an event E, we can determine the probability that the event will not occur. The event not E is the complement of E because it is the set of all outcomes in the sample space that are not outcomes in the event. Thus, we have these rules. Remember when we first talked about our fundamentals of probability and we said the sum of all the probabilities of a sample space always add to 1? Well, that means the probability of your event happening plus the probability that the event does not happen equals 1. And from this equation, we can solve for the probability the event does not happen or the probability the event does happen and get these two. For example, let's say what's the probability that you roll a 5 if you are rolling a simple 6-sided die. Since there's 1 5 on the die out of 6 sides, the probability is 1/6. But the probability that you do not roll a 5 then is how many numbers are not a 5? Well, 1, 2, 3, 4, and 6. So 5 numbers are not a 5 out of a total of 6. Okay, notice that this is 1 minus 1/6, right? Or 6/6 minus 1/6 gives us that 5/6. Come on. What's happening? Gives us that 1/6. Okay. Suppose that you randomly select one card from a deck of 52 cards. Let A be the event of selecting a king and B be the event of selecting a queen. Only one card is selected. Now remember, we've mentioned that before. That's important to pay attention to how many cards are being selected. Only one card is selected. So it is impossible to get both a king and a queen. The events of selecting a king and a queen are called mutually exclusive, which means it is impossible for events A and B to occur simultaneously. In general, if A and B are mutually exclusive events, the probability that either A or B will occur is determined by this formula. So notice from our example, we want to know what's the probability that you get a king or a queen. Well, in this case then, it would just be the probability that you get a king plus the probability that you get a queen because those events are mutually exclusive. So the probability you get a king, 4 kings out of 52, plus the probability you get a queen, 4 queens out of 52, or 8 out of 52. Okay, which is what? 2 out of 13. Oh yeah, out of every 13 cards, there's a king and there's a queen. 2 of those cards out of 13. Now, suppose that you randomly select one card from a deck of 52 cards. Let A be the event of selecting a king and B be the event of selecting a diamond. If we want to find the probability of A or B in this case, it is not just a matter of adding their individual probabilities. Since there is one card that is a king and a diamond simultaneously, these events are not mutually exclusive. So in general, if A and B are not mutually exclusive events, here's the formula for that probability. Now, notice for the king of diamonds, we've counted it in the probability that it's a king, and we've counted it in the diamonds. So we have to take one of those occurrences away. If I wanted to know what's the probability that I'm going to get a king or a diamond, a king, let's change that just so that it looks more standard and a little bit, a king and a diamond, then it's the probability that our card is a king plus the probability that the card is a diamond minus the probability that the card is a king and a diamond simultaneously at the same time. So the probability it's a king, there's still 4 kings out of 52. The probability that it's a diamond, now there are 13 diamonds out of 52, minus the probability it's a king and a diamond. So I got to figure out how many cards are kings and diamonds. Well, 1, the king of diamonds. So I counted it here and I counted it here. I don't want to count it twice. So 13 minus 1, 12 plus 4, so 16 out of 52. Simplify that, divide each of them by 4. 4 13ths. Now notice that didn't get much better. Okay, notice this is the formula for an OR probability when events are mutually exclusive. This is an OR when they're not mutually exclusive. But really, this one right here is really the only one I need to be concerned with. Because if 2 events are mutually exclusive, the probability of A and B equals 0. Just like the probability of getting a king and a queen on one card, that's 0. So I can plug in here and I'll just subtract 0 to give me the exact same answer. But here's a formula, and here's a formula that we need to write down somewhere and memorize before the test. And then, if we know the probability of an event, we can also speak of the odds in favor or the odds against the event. Okay, the following definitions will link together the concepts of odds and probability. So if the probability of E, if this notation is the probability of an event E occurring, then the odds in favor of E are found by taking the probability that E will occur and divide it by the probability that E will not occur. The odds against, we take the probability that E will not occur and the probability that E will occur. A lot of times people use the words probability and odds interchangeably. Okay, like what are the odds that happen when they're really talking about the probability? Let's look at the difference of between those two. Let's say, again, let's go back to something simple. So the probability that you roll a 5 on a simple 6-sided die, we know is 1 out of 6. But the odds that you're going to roll a 5, so the odds in favor, the odds that you are going to roll an E, notice if we plug into the formula, let's see what we get. Okay, odds for is the probability that the event happens, so 1/6, over the probability that it does not happen, 5/6, which is 1/6 divided by 5/6, or 1/6 times 6/5, 1/5. Typically, to keep odds and probability separate, we usually write odds in the ratio form as 1 to 5 or 1 to 5. Let's talk about the difference between the probability of your event happening and the odds for your event happening. The probability is comparing how many ways your event can happen to every total possible way. Odds is comparing how many ways your event can happen to how many ways your event cannot happen. So there's the distinction between probability and odds. Now, if we were going to do the odds against, to plug into the formula, right, then we would do the probability that it does not occur over the probability that it does occur. So again, 5, 6 divided by 1, 6. And to divide fractions, we make it multiplication and use the reciprocal of the second one. So we have 5 to 1. Notice that once we had the odds that it would occur, we also had the odds against that event occurring. They can be found by reversing the ratio representing the odds in favor of the event. Also, a lot of times I don't really have to plug into this formula here and evaluate that. I know what it means to be odds. It's the number of ways the event can happen compared to the number of ways it cannot. The odds against is the number of ways it cannot happen compared to the number of ways it can happen. So if I were talking about the odds against rolling an even number, right? Well, how many ways can I roll an even number compared to how many ways can I not roll an even number? So 1 to 1, just like in any fraction, it has to be simplified. Also notice that I keep the 1 in the odds because odds is a comparison of two quantities. So I want to keep that 1. I would never say the odds against something is 5. It's 5 to 1. Okay, odds enable us to play and bet fairly on games. For example, we have seen the odds in favor of getting a 2 when you roll a die are 1 to 5. Suppose this is a gaming situation and you bet $1 on a 2 turning up. In terms of your bet, there is one favorable outcome, rolling 2, and 5 unfavorable outcomes, rolling a 1, 3, 4, 5, or 6. If the odds in favor of an event E are A to B, so for example, the odds in favor of rolling a 2 are 1 to 5, then the game is fair if a bet of, in our case, $1 is lost if event E does not occur, but a win of, in our case, $5, as well as returning the bet, is realized if event E does occur. So here's that again. For example, if you bet $1 on a 2 turning up and the game is fair, you should win $5 and have your $1 returned, of course, if a 2 turns up. The odds given at horse races and at all games of chance are usually odds against. If the odds in favor of a particular horse winning a race are 2 to 5, then the odds against winning are 5 to 2. At a horse race, the odds on this horse are given simply as 5 to 2. The house odds tell a gambler that the payoff is on a bet. For every $2 bet on the horse, the gambler would win $5 if the horse won, in addition to having the $2 bet return. So the odds they post, right, tell a gambler what the payoff is. Let's look at some questions. What about this? You are dealt one card from a 52 card deck. Find the probability that you are not dealt an ace. Okay, so the probability that we're not dealt an ace. Well, one thing I could do is I could count up how many cards are not aces. But it's usually way easier to count up how many cards are aces. So I know that the probability of an event not happening is 1 minus the probability that it does happen. And there are 4 aces out of 52 cards. So 1 minus 4 out of 52 is 48 out of 52. Okay, don't forget to simplify that. 12 out of 13 is the probability that you will not be dealt an ace. What's the probability that you will not be dealt a heart? Well, it's 1 minus the probability that you will be dealt a heart. Or 1 minus 13 cards are heart, 52 total cards. So 52 over 52, right? Get that common denominator. 1 minus 13 over 52. What's that give us? 39 over 52. Let's see. Does that simplify? Um, 39 over 52. Okay. Oh, no, 13. I was thinking it should. Okay, 13. So 39 divided by 13 is 3. Okay, you randomly select one card from a 52 card deck. And remember, your calculators will do that simplification for you. You randomly select one card from a 52 card deck. Find the probability of selecting a 2 or a 3. All right, probability that you get a 2 or a 3. Well, that's a formula, remember. It's the probability that you're going to get a 2 plus the probability that you're going to get a 3 minus the probability that it's a 2 and a 3. Okay? Which in this case, because they're mutually exclusive, a card cannot be a 2 and a 3. That's simply 0. So the probability that it's a 2, there are 4 2s out of 52. There are 4 3s out of 52. And because no cards are 2s and 3s, there's nothing to subtract. So 8 out of 52. Or that simplifies to both of these are divisible by 4. So 2 out of 13. What's the probability that you're going to get a, let's do that this way, a red 7? Okay. Or a black 3, just to save us some space here in my writing. Well, that's the probability that we're going to get a red 7. We're going to get a red 7 plus the probability that we're going to get a black 3 minus the probability that we're going to get a red 7 and a black 3. Okay, and I noticed that a red 7 and a black 3 are mutually exclusive, so that's just going to be 0. So the probability that it's a red 7, there are 2 red 7s, the 7 of hearts and 7 of diamonds, out of 52 total cards. Likewise, there are 2 black 3s, 3 of clubs, 3 of spades, and no cards that are black and red or 7 and 3, either way you want to look at it. 4 out of 52 or 1 out of 13. Okay, one more of these. What's the probability that you get a 7 or a red card? Okay, now these are not mutually exclusive. There are some cards that are 7 and red. So this is the probability that your card is 7 plus the probability that your card is red minus the probability that it's 7 and it's red. Well, the probability that it is 7, there are 4 7s out of the 52 cards. There are half of them are red, so 26 red, 13 diamonds and 13 hearts, and 2 cards are 7 and red, right? So I've counted both of those here, and I've counted both of them here. So I need to readjust my count. So this is 26 plus 4, 30 minus 2, 28 out of 52. Both of these are divisible by 4, so 7/13 is the probability of being dealt or selecting a 7 or a red card. What about this one? A single die is rolled. Find the probability of rolling an even number or a number less than 5. Okay, so probability that it's even or less than 5. Well, that's the probability that it's even plus the probability of rolling a less than 5 minus the probability that it's even and less than 5. So the probability that it's even on a single die, 2, 4, 6, there's 3 ways out of 6 of rolling an even number. The probability that it's less than 5 would consist of the sample space 1, 2, 3, 4. So there's 4 out of 6 ways to roll a number less than 5. Now, these are not mutually exclusive, so this is not 0. So I've got to figure out how many of them are even and less than 5. Well, my even numbers are 2, 4, and 6. So 2 and 4 are both even and less than 5. 2 ways that a number can be even and less than 5. So 7 minus 2 is 5. 6 is the probability of rolling on a single die an even number or less than 5. The mathematics faculty at a college consists of 8 professors, 12 associate professors, 14 assistant professors, and 10 instructors. If one faculty member is randomly selected, find the probability of choosing a professor or an instructor. Well, again, with an or probability, that's just a formula I've got to memorize. It's the probability of getting a professor plus the probability of getting an instructor minus the probability of getting a professor or an instructor. In this case, those are mutually exclusive events. You're not a professor and an instructor, right? Those are different titles. You're either a professor or you're an instructor. You're not both. So it's just the probability of being a professor, and there are 8 professors out of the total number of faculty. So 20, 30, 44, 8 out of 44, plus the probability of being an instructor, and there are 10 instructors out of 44. This is 0, so minus 0. So 18 out of 44. They're both divisible by 2, so 9 22nds. Let's see what else we have. Come on, what happened? Okay. The mathematics department at a college of 8 of a college has 8 male professors, 11 female professors, 14 male teaching assistants, and 7 female teaching assistants. If a person is selected at random from the group, find the probability that the person is a teaching assistant. So we'll see say a teaching assistant or a female. Well, that's the probability that the person is a teaching assistant plus the probability that the person is female minus the probability that the person is a TA or, not or, excuse me guys, and female. Okay, so the probability that the person is a teaching assistant. Okay. There are 14 male teaching assistants and 7 female teaching assistants for a total of 21 teaching assistants out of plus 19, so it looks like there's 40 total people in the mathematics department. 20, 34, oh, okay, 19, 26, yeah, 40. Okay, and there are 14 plus 7, 21 teaching assistants, plus the probability that that person is female. Now, I've got 11 females that are professors and 7 females that are teaching assistants. So 11 and 7, there's 18 females out of the 40. Now, how many are teaching assistants and female? Well, there are 7 female teaching assistants out of the 40. So a total of 18 minus 7 is 11, so 32 40ths. Divide each one by 8, 4/5. The table above shows the educational attainment of the U.S. population ages 25 and over. Use the data in the table, which is expressed in millions, to find the probability that a randomly selected American aged 25 or over has not completed 4 years or more of college. So the probability that 4 or more not is 1 minus the probability that they did complete 4 or more years. All right, so 1 minus, when I look up here, I got to find the probability that a randomly selected person completed 4 or more years. 45 million out of 174 million. 45 out of 174 million. Again, we can plug that in our calculator, but what we're really doing is getting a common denominator, making that 1. 174 over 174. And then once we have the denominator the same, we simply subtract the numerator. So what would that be? 129. Let me double check. Okay, so 129 over 174. Okay, looks like these are both at least divisible by 7, 8, 9, 11, 12. Yeah, by 3. So let's see what that simplifies to. And remember, you can plug that in your calculator and simplify it. So 43 out of 58. All right, looks good. Hopefully. Find the probability that a randomly selected American, age 25 or over, has completed 4 years of high school only or is a man. So probability 4 years only or a man. Well, that's the probability that they did 4 years only, plus the probability that they're a male, minus the probability that they did 4 years and they're a male. So let's see what this is. Probability of 4 years only. 4 years of high school only is 56 out of the total 174. The probability that the person is a male, here's my male row, is 82 out of 174, minus the probability that it's 4 year only and a male. Here's my males with 4 years of high school only. So 25 out of 174. All right, we've got that common denominator. Let's just, I'm going to plug this in the calculator this time just for expediency. So 56 plus 82 minus 25, 113. Okay, 113. I'm going to let my calculator see if that'll simplify. No. Okay, let's see what we have here. A single die is rolled. Find the odds in favor of rolling a number greater than 2. Okay, my odds in favor, technically, and we'll do this a couple of ways to start with. It's the probability that you roll a number greater than 2, so 3, 4, 5, 6, so 4 out of 6, over the probability that you do not, so 2 out of 6. Notice these 6's are going to divide out and give us 4 out of 2 or 2 to 1, right? So you may want to write that like that. Look and see how your homework wants you to enter it. 2 to 1. Or I could have realized what it means to be odds and just count how many ways you can get a number greater than 2. So 3, 4, 5, 6, 4. And how many ways are not greater than 2, the 1 and the 2, which has to be simplified, right? Okay, notice once you have a probability, you can get the odds, and once you have an odds, you can get the probability, because these add up to your total number of ways that's possible. So let's talk about that over here. Find the odds against rolling a number greater than 2. Well, if I've got the odds for rolling a number greater than 2, I don't have to recalculate anything. I've got the odds against 1 to 2, which means I have the probability you're not going to roll a number greater than 2. It's 1 out of 3 if it asks me that, right? 1 out of, add them together, 3. One card is selected at random from a deck of cards. Find the odds in favor of drawing a heart. So I got to think of how many cards are hearts. There are 12. And how many cards are not. There's not 12. There are 13. Right? 13. And how many cards then are not hearts? 13 are hearts, meaning 52 minus 13, 39 are not hearts. So the odds in favor of drawing a heart, again, you got to simplify this, 1 to 3. Okay, if I wanted the probability, if I knew this and I wanted the probability of drawing a heart, it's 1 out of 4, right? Add these together. I also know now the odds against drawing a heart are 3 to 1. And the probability against drawing a heart is 3 out of 4. Okay, find the odds against drawing a black king. So how many cards are not a black king? Well, 2 of them are a black king. So 50 of them are not a black king. And 2 of them are a black king. Right? So 25 to 1. Again, if you have a little bit of trouble with these larger numbers, go back to your formula. The probability that you don't draw a black king. So the probability that it's not a black king, I still have to count up then how many are not a black king, but I also have this formula for a probability of, let's write it like this, say not a black king, is 1 minus the probability that it is a black king. So I can get that from 1 minus, okay, so how many are Black Kings. There are 2 Black Kings out of the 52. Oh, so there are 50 out of 52 that are not Black Kings. So use these methods together and whatever makes your math the easiest for you. And if we were using the formula, then it's the probability that's not a Black King over, I've already calculated the probability that it is a Black King. And then just continue to simplify. Of the 38 plays attributed to Shakespeare, 18 are comedies, 10 are tragedies, and 10 are histories. 1 play is randomly selected from Shakespeare's 38 plays. Find the odds in favor of selecting a comedy or a tragedy. All right, so I've got to see how many of them are a comedy or a tragedy. Or if you're following the formula specifically, find the probability of it being a comedy or a tragedy, which those are mutually exclusive, right? The plays are not comedies and tragedies. They're classified as one or the other, but not both. So I would just count up, well, how many are comedies or tragedies? 18 comedies, 10 tragedies. So 28. And then how many are not? Right? And 10 are histories. 28 to 10, and don't forget to simplify that to 14 to 5. Against selecting a tragedy or a history, right? It's not saying against this. If it said against selecting a comedy or a tragedy, I know it's 5 to 14. But now it's asking a different question. Find the odds against selecting a tragedy or a history. So how many are not a tragedy or a history? 18 are comedies. Compared to how many are tragedies or histories? 20. So in this case, 9 to 10. Okay, that finishes this section up. Let me know if you have any questions.